Welcome back. In today's lecture, we'll discuss the how to calculate the potential due to concentric charged shells and how to find out induced charges on those shells. Let's proceed with it. We have already studied that if it's a conducting solid sphere or a hollow shell, charged shell, and it has got some charge on it, say Q. What is the value of potential at a point outside it, on it, and any other point inside it? We know, let's say, we wish to find out electric potential at a point which is at a distance x from the center of the shell or conducting sphere. Then the potential at this point, let's say I call that point P. Potential at P is 1 by 4 pi epsilon naught Q by x. For simplicity, from now onwards, I'll skip 1 by 4 pi epsilon naught and simply call it K Q by x. If I wish to find out electric potential on the surface of this shell, let's say I call this point Q, then BQ is equal to K times Q by R, where R is the radius of the shell. And what about any point? Let's call that point S. Any point inside S. S may be here, or anywhere else inside this shell. At all points, the potential would be same as it was on the surface of the shell. This is we have already done. Now, think of a problem when instead of one shell, we have got multiple shells. Let us take, for example, 3 concentric shells. Let's say these are 3 shells. Let's say the first shell has got radius A, the other shell has got radius B, and the third shell has got radius C. And I wish to find out electric potential at a point which is completely outside of all the 3 shells. Let's say this is P, some other point, let's say I call that M, this point over here as N, and somewhere over here, let's say D. I wish to find out electric potential at a point P, M, N, and D. And then I'm assuming that this first shell has got charge QA, the second shell has charge QB, and the third shell has got charge QC. Now, first of all, let's start with point P. The point P is at a distance x from the center of the first shell, the innermost shell. Now, the electric potential at P should be the algebraic sum of potentials due to the first shell, due to the second shell, and due to the third shell. Potential is a scalar quantity, so we need to take just their scalar algebraic sum. So what is potential at point P? So first of all, let's find out potential at P due to the first shell. For first shell, the point P lies outside it. So potential at P should be equal to K times, K I am taking as common, QA divided by X. Because for the first shell, the point P lies at a distance X from the center of the shell. Now, what about the potential due to the second shell? It would be QB by X and similarly QC by X. Why I am taking the distances to be X only? Because for, let's say, shell number C, shouldn't the distance be C minus X? The answer is no. Because we know that outside the shell, it seems that the charge is concentrated at the center of the shell. Therefore, even if I am considering point P very close to shell C, but since I am outside the shell C, from point P, it will seem as if whole of the charge is at the center. So distance would still remain x. So potential at P is sum of potential due to first shell, second shell, and third shell. This is the expression. The things will change when I go to point M. Let's see what is potential at point M. K as usual is constant. For shell A and shell B, point M is outside. And now let's say the distance of point N is x. This is distance x. For point M, the distance is x and it is outside the shell A and B, but for shell C, the point M lies inside the shell. So for for the shell A and B, the things are not very much different. This will be QA by x plus QB by x. But what about the potential due to the third shell? For third shell, point is inside the shell. Therefore, the potential at a point inside the shell is same as the potential on the surface of the shell. So it will become QC divided by the radius C. Let's say we wish to find out potential at point N, and now I am considering the N to be at a distance x from the center of the innermost shell. Now, point N is outside the shell A, but it is inside shell B and shell C. So what should be the potential at point N? It should be QA divided by x plus QB by B plus QC by C. And similarly, what about potential at point D? Now point D is point D is inside all the three shells. So the potential at D due to first shell would be QA by A plus potential due to the second shell will be QB by B and potential to the third shell will be QC by C. That is, when the point lies inside a shell, what you need to do, you don't calculate its distance from the center of the shell, rather you calculate the potential at the surface. And this is a very good example and a very important one as well. But things become even more interesting when we are asked to find out the induced charges on these shells when one of the shells has been grounded. Let's take a very standard question. Let's say this is a shell which has got radius, let's say A, and I've given it charge Q. Then there is a second shell. It is also a thin shell, but I am showing a small thickness for it. You will come to know about it, why I have done it. This is the second shell. Even if it is thin, it has got some finite thickness. And let's say its average radius is B, and it has been grounded. And there is a third shell again, and again for the same reason I am considering some thickness for it, and charge minus Q is given to this shell. Now as Q charge appears over there, due to this Q charge, some charges would be induced on the inner surface as well as some charge will appear on the outer surface of this second shell. And similarly, some charge will appear on this inner shell and inner surface of this third shell, and some induced charge will develop on the outer surface of this shell. You need to find out these charges. Let's say I call these charges whatever, QA, and let's say I call this QB, I call this QC, and I call this QD. We need to find out the charges, induced charges on these shells, that is QA, QB, QC, and QD. This is the question. While solving these questions, you should keep three things in mind. There are 3 points which you need to apply to solve these kind of questions. Number 1. If a charge is isolated and is not connected to anything else, and you bring something close to it, the induced charges may appear, but they will appear in such a way that the total charge on the isolated surface cannot change. That means consider this innermost shell. Now, since you have put an outer shell as well there, and some induced charges have appeared, but total charge on the innermost shell Q will remain Q. Similarly, the total charge on the outermost shell is minus Q, that will remain minus Q. The shell which is connected to ground may increase or decrease in charge simply because that's not isolated, that is connected to something else. So charges can flow from it, or that charges can come to it. So charges on those spheres can change in magnitude, but the total charge on an isolated body would remain conserved always. This is the first point. The second point we should consider is that the potential, the electric potential on the shell which has been grounded must be zero. The ground potential always remains zero. This is the second point we need to apply. And the third was, since these are conducting spheres or concentric shells, inside the shell the field is always zero. That means that if you apply E dot ds is equal to Q net, the net charge inside the Gaussian surface, over epsilon naught. Since electric field is zero, it is easy to say that Q net would always be zero on our Gaussian surface. So let's proceed with the second sphere. I wish to find out QA and QB first of all. So what I was doing, I had considered its finite thickness. This was done simply because I want to draw a Gaussian surface inside it. As I told you that Q net should be zero, if charge Q is over here and charge QA is over here, and this is the Gaussian surface, inside the Gaussian surface, the Q net must be zero. That means Q plus QA should be equal to 0. Q and QA must be equal to 0. So it is easy to say that QA is equal to minus Q. QA is equal to minus Q. So I replace this thing with minus Q. What about QB? I don't know. I don't know yet. So I have kept it QB only. Let's now proceed to the third shell. And let's say I draw another Gaussian surface. I draw another Gaussian surface. Let's see what will happen. It has got the inside this Gaussian surface, Q net must be 0. So what is the total charge inside this Gaussian surface? It is Q over here, then minus Q over here, then QB over here, then QC, and that's equal to 0. Again, I find that QC is equal to minus QB. But I don't know about QB yet, therefore I don't know about QC as well. So this is QC, and QC, I am replacing it as minus of QB. What about QD? Since this shell is an isolated shell, the total charge on it should remain conserved, point number 1. So charge on it is QD and then minus QB, and then that should remain equal to minus Q. QD and minus QB should remain equal to minus Q. Or in other words, what you can say, the total charge should have remained minus Q. This means that I should say it like this: minus Q should remain minus Q. That means that QD is equal to QB. The total charge on it is QD and minus QB and minus Q, but that should remain equal to minus Q. That means the sum of induced charges must vanish. So if it was minus QB, that has to be QB. So that the total charge is now minus QB, minus Q, minus QB plus QB, that get cancelled and that remain minus Q only. Now the problem gets limited to one point. What is the value of QB? If you can find out QB, then you have obtained the induced charges on all the shells. Let's proceed with that, and that would be done by the second point which we did, that the grounded shell must have potential equal to 0. So the total potential on the second shell is potential due to the A shell, due to B shell and due to C shell, and that should be 0. So let's find out potential at this. Its radius is B. This will be equal to, due to this, it will be Q by B times K. I am taking K common. It will be Q by B. Then I'll have minus Q by B. Then I'll have plus Q by B. Then I'll have minus QB by C plus QB by C, and then minus Q by C. Whatever get cancelled out. B is equal to K times Q by B minus Q by C, and that should be equal to 0. That should be equal to 0. I think this point was not correct. This was QB by C. QB by B. So this is QB by B, and let's solve it out. QB by B is equal to Q by C. So QB is equal to B by C times Q. Let's take a numerical problem. आपको given charge is 10 coulomb to this, minus 10 coulomb to this, and the second shell has been grounded. Let's say the radius are 1 meter, 2 meter and 3 meters. So what are the induced charges on these shells? If it is 10 coulomb, the inner shell will have minus 10 coulomb. If it is Q, it is minus Q. And on the outer shell, what would be the charge? That will be calculated by this formula. QB will be equal to B by C. In this case, B by C becomes 2 by 3 times the total charge, that was 10 coulomb. So it becomes charge on the outer shell, outer second shell will be 20 by 3 coulombs. Then charge on the inner shell is minus QB. So it is minus 20 by 3 coulombs, and on the outer shell it would still be minus 10 coulomb and plus 20 by 3 coulomb. That's the answer. Thank you.